Hi, this is Alex from devstories.eu. LangGraph, episode 13 of 18. You build an agent and a user tells it they always want their code in Python 3.11. Tomorrow, they start a new conversation and the agent completely forgets outputting Python 3.9 instead. Thread memory is isolated to a single conversation. When your agent needs to retain facts across entirely separate sessions, you need long-term memory using stores across threads. A common mistake is trying to solve this by stuffing long-term facts into the checkpointer state. Checkpointers are short-term memory. They are strictly per-thread state snapshots designed to pause, resume, or replay a single conversation. If a user states a preference in thread A, thread B has absolutely no way to see it. To share knowledge across multiple threads, LangGraph provides the store interface. A store is a key value memory layer that sits outside individual thread states. You set it up by passing a store object, like a Postgres store, as an argument when you compile your graph. Once compiled, that store is attached to the graph execution environment. Inside your graph, nodes access this memory layer through the runtime object. When you define a node, you can access the runtime context, which exposes the store. You simply access runtime.store to interact with your long-term memory. Here is the key insight. Data in a store is organized using namespaces. A namespace is a hierarchical list of strings that partitions your data, much like a folder path on your computer. For a multi-tenant application, you might define a namespace that starts with the string users, followed by a specific user ID, and ending with preferences. Think about that coding assistant scenario. A user starts a session on Monday. During the chat, they mention they prefer Python 3.11 and dark mode. A node in your graph recognizes this as a permanent preference. It calls the put method on runtime.store. It passes the namespace for that specific user, a unique key for the item, and a dictionary containing the preferences. The data is now saved outside the thread. On Friday, the same user opens your application and starts a brand new thread. The checkpointer state for this new thread is completely empty. However, your graph includes a setup node that runs first. This node calls the search method on runtime.store, providing the user namespace prefix. The store returns the saved preferences. The node then places those preferences into the current thread state. From that point on, the agent knows to use Python 3.11 and dark mode for this new conversation. The store interface provides three main operations. You use put to save or overwrite an item. You use get to retrieve a single item when you know its exact namespace and key. You use search to retrieve multiple items that share a namespace prefix. Searching is particularly useful when you have saved several distinct memory fragments for a user over time and need to pull them all into the current context. By separating short-term state from a cross-thread store, you decouple the lifespan of your agent knowledge from the lifespan of a single conversation. Appreciate you listening. Catch you next time.